Okay, so today we were looking at antidifferentiation. So I'll just go over some of the main ideas in that lesson today. Antidifferentiation, as the name implies, is the opposite of differentiation. So what we've done previously, we're trying to almost like undo it. Another term is integration that you will hear, which means the same kind of method that you're using. So the big idea is that in differentiation you're finding the gradient of the curve at a point. One point on the curve you want to find the gradient, so you differentiate. With anti-differentiation or integration, you're finding the area under a curve. So between 2 points you're finding, say for example, if I put a line here and here, between x1 and x2 you're finding that area between the x-axis and the curve. And you can imagine this is very helpful in engineering and physics, mathematics, when you're finding the area under a curve. You'll do more of this next year. We talk about integrals. We find the integral of a function or expression between 2 points. For now we're just going to stick with anti-differentiating. So the symbol is this elongated S that you find at the beginning with a dx after the expression. If a function of x is x squared, what we've done before, differentiating that f dash x becomes 2x. If we do the opposite of that, we're going from the 2x back to the x squared. And we write it like this below: the integral, using that symbol, by the integral of 2x with respect to x is x squared plus some constant. C is the constant of integration. Let's look at the next. So our rule for anti-differentiation, we add 1 to the power. The index n is going to be plus 1, and then we divide that term by n plus 1, and then we add a constant to the end of the expression. So some examples here will do. We're integrating 6x squared with respect to x, so that equals 6x. 2 plus 1 is 3, we divide it by 3 as well, and we add a constant. Okay, and we can of course simplify that to 2. 6 divided by 3 is 2, so 2x to the power of 3 plus c. This one here, we're going to have 3. Our x to the power of 2, we're going to add 1, so it's x to the power of 3 divided by 3 plus 6x to the power of 1 plus 1 would be 2 divided by 2 minus 5. Now this is like an x to the power of 0, so it becomes an x to the power of 1 over 1 plus the c. Now again, you can simplify these. 6 divided by 2 is 3. Our last example here, x to the power of 4 will become x to the power of 5 divided by 5 plus 6 in the front. X to the power of 5 plus 1 is 6 divided by 6, those will cancel, plus 4x to the power of 1 becomes x to the power of 2 divided by 2, and you can simplify that, plus a constant. And we'll look at the constants in a little bit. Okay, there's those examples. Here is another, when we get a little bit more complicated, if you find that you've got brackets or fractions, then you need to expand the brackets, or simplify our expressions before we integrate. So if I have x squared outside the bracket, I'm going to multiply everything by the x squared. You can see I've done that here. And so then we go ahead and integrate that. So our 2 stays in the front, x to the power of 4 divided by 4 minus 5x to the power of, that will become power of 3 over 3 plus our constant. Integrating here, we've x squared plus 5 divided by x. Each term is divided by x, so I've made that into 2 fractions divided by x, and then I've use a different colour. I've actually simplified this, x over x, so I've ended up with x plus 5. Integrating this with respect to the dx, x to the power of 1 will become x to the power of 2 divided by 2 plus 5, that's like an x to the power of 0, will become x to the power of 1 over 1 plus c. And the last expression here, we've got a quadratic. We multiply that out, expand it, so that we've got that with respect to dx is x to the power of 3 divided by 3 minus 10x to the power of 2 divided by 2 plus 25. You can see you get into a pattern of doing this, plus c. Okay, I hope you can do lots of practice on that. Look in the textbook, look in your workbook, and work on practicing that. Okay, so finding the constant of integration. Basically, you'll be given the gradient equation, and from that you'll also be given a coordinate point that's on the graph. From the coordinate you can work backwards. So looking at this one, we know that the gradient function is 2x minus 9. We want to find the function. So we integrate, we go backwards. So the integrating 2x minus 9, we're going to have 2x to the power of 2 and divide by 2 minus 9x plus some constant. I can simplify that to x squared minus 9x plus c is my function. Now I know when x is 1, I have an answer of 5. So let's put x is 1 in. So 5 equals 1 squared minus 9 times 1 is 9 plus c. So 5 equals 1 minus 9 is negative 8 plus c. I'm going to solve this, put 8 on the other side. So 5 plus 8 equals c. C must equal 13. Okay, so I'm looking here, they've asked me for the constant of integration, so the constant is 13. 1. Here we're told, this is the kind of example you'll be given, a curve passes through the point negative 2, 3, and the gradient function is this function here. Find the equation of the curve. So I'm going to, in blue here, are my workings, I'm going to integrate the gradient function, and so I'll end up with 3x to the power of 3 divided by 3 minus 8x to the power of 2 over 2 plus 1x plus c. So my y equals x to the power of 3, I'm going to simplify that, I had dy over dx, so now I've got y left. Minus 4x squared, when I simplify that, plus x plus c. Now I know that I've got this point here where my x is -2 and my y is 3. So 3, substituting in, equals -2 to the power of 3 minus 4 times -2 squared plus -2 plus c. 3 equals -2 cubed is -8. 2 2s are 4, 2s are 8. -2 squared is 4, so it's -16 plus a -2 plus c. So 3 equals -26. It's a 6 plus c. I'm going to transfer this onto the other side so that I have 3 plus 26 equals c. C equals 29. Hope that's right. We've been asked for the equation of the curve. I've found my constant. So this was the equation, and here I've just got to put the c in. So y equals x cubed minus 4x squared plus x plus 29 would be the equation of the curve.